Hey, in this tutorial we're going to be looking at other algebraic functions. Okay, so the first one we're going to look at is the hyperbola. Okay, now that has a general equation, or just a very basic equation of y equals 1 over x, or y equals x to the power of -1. Now our general graph looks like this. Okay, so we've got our axes here, our y and our x-axis. Okay, and we've got this curve here and this curve here making up the graph. Okay, we also have a horizontal asymptote, there's the x-axis, and a vertical asymptote, there's the y-axis. Okay, you can see that here. So a vertical asymptote is when x equals 0, horizontal when y equals 0. For this, the domain and range are both all real numbers excluding 0. Now that's what our basic one looks like. Okay, we can take this further though and look at it in power form. Okay, very similar to all our other polynomials in power form, it's just this time our power is -1. Okay, so we find that we have a vertical asymptote at x equals h now, because remember h is our horizontal translation. We have a horizontal asymptote at y equals k, because again k is our vertical translation. Okay, and our asymptotes intersect at the point hk. So previously with our power functions where we had to the power 2, 3, 4, okay, then our point hk was either a turning point or a point of inflection. Now if you like, it's where our asymptotes intersect. Okay? The domain is all real numbers excluding h, and the range is all real numbers excluding k. Okay, so we'll have a look at a worked example for this one. Okay, the one that I'm actually going to do is looking at worked example 7 part B. Okay, so for this one we have the function y equals 2x plus 5 over x plus 1. Okay, and so we want to find the maximum domain, or the maximal domain of this. Okay, so we need to be thinking about when is the function undefined. Okay, so the function is undefined, okay, when the denominator equals 0. So when the denominator equals 0, we get x plus 1 equaling 0, therefore x equals -1. Okay, so that means that we've got to exclude -1, okay, from our domain. So our maximal domain for this would be all real numbers excluding -1. Okay, and the other part is of this question is we need to sketch a graph and state the range of the function. Okay, so the thing is, when we look at this, it looks very, very different to what we had previously. So what we need to do, okay, is actually express this equation in the proper rational form, okay, because we don't like it like that. So what we basically have to do is we want to end up with a term up in the numerator that is x plus 1. Okay, and the way we do that is really we just go, well, we can't have this 2, so that's a problem. Okay, so we're going to bring that out, okay, and we're going to put in our term x plus 1 that we wanted. Okay, we know this is going to be over x plus 1. Okay, and now you need to go, okay, well if we expanded this bracket, okay, we get 2x, which we needed, plus 2, but we actually need plus 5. So what we do is we actually go plus 3. So now the top line is everything that we need. So what we do then is we split this into two fractions. Let's say we've got 2 outside of x plus 1 over x plus 1 plus 3 over x plus 1. We get y equals, we're left with our 2, we'll put that at the end and say that we've got 3 over x plus 1 plus 2. Okay, so that's in our proper rational form. Now we've been writing it though as 3x plus 1 to the power -1 plus 2. Okay, so that's in the form that we've been used to seeing. Okay, so that means that we can see that we end up with a vertical asymptote. Okay, vertical asymptote at x equals -1, okay, because we've got to change our sign to this one. Our vertical oops, sorry, just did the vertical, we want the horizontal, don't we? The horizontal asymptote at y equals 2. Okay. We do have that dilation factor of 3. Okay, but that doesn't matter too much at the moment. What we do want to do though is find our x and y intercepts. Okay, because as soon as we translate it at all, then we're going to have our intercepts. Okay, so because we translate across, we'll have intercepts. So we need to let y equal 0. Okay, we may as well use this one. Okay, so we say y equals 0. So 0 equals 3 over x plus 1 plus 2. We get negative 2 equals 3 over x plus 1. Okay, we can multiply by x plus 1 and divide by negative 2. So we get x plus 1 going 3, negative 3 over 2. Okay, so we get x equals negative 3 over 2, take 1. X equals negative 5 on 2. Okay, so we get our x-intercept at negative 5 on 2. Okay, and to get our y-intercept, okay, we let x equals 0. So this time we'll go y equals 3 over 0 plus 1 plus 2. Okay, so y is going to have an intercept at 5. Okay, so we know all the information that we need now, okay, to actually sketch our function. So we know we've got a vertical asymptote at negative 1. Okay, that's at negative 1. We have a horizontal asymptote at 2, y equals 2. Right, and we know we have a y-intercept up at 5. Okay, and an x-intercept at negative 2.5. Okay, and now I can draw our graph. Be something like this. Okay, and of course we need to label our axes. Okay, alright, we'll keep moving on. So the next one we're looking at is the truncus. Okay, so its general one is y equals 1 on x squared, or y equals x to the power negative 2. Okay, it's called a truncus because it kind of looks like the trunk of a tree. Okay, again we have a horizontal asymptote that is the x-axis and a vertical asymptote that is the y-axis. Right, and so again our vertical asymptote is x equals 1 and our horizontal asymptote is y equals 0. Okay, our domain is all real numbers excluding 0. Okay, but our range is all real positive numbers, okay, because we are including everything above the x-axis. Okay, so in power form, okay, we're looking at y equals a outside of x take h to the power negative 2 plus k. Our vertical asymptote is at y equals k. Sorry, that's not right. They're around the wrong way. So our vertical asymptote is going to be at x equals h, and our horizontal asymptote is going to be at y equals k. Our domain will be all real numbers excluding our h value. Right, and when a is bigger than 0, okay, then the range is going to be from k to infinity. And when a is less than 0, the range is going to be from negative infinity to k. So when a is bigger than 0, a is positive. The graph is going to look like this. When a is negative or less than 0, it's going to be reflected in the x-axis. Okay, so we'll flip over and we'll have a look at doing a work example for that one as well. Okay, so for this we want to sketch a graph of y equals 8 minus 2 over x take 3 squared, okay, and state the domain and range. So I'm going to actually rewrite that and write it in the form of that. Okay, so all I've done is I've put okay, a constant at the end, and made it -2 out the front. So as we've just seen, because this a value here is negative, we're going to be a graph that has been reflected in our x-axis. Okay, so what we need to do, because they've been translated, we need to find our intercepts. So we'll say y-intercept. Okay, remember we let x equal 0, and that should be to the power -2. Okay, so when we do that, we get y equals -2 outside of -3 to the power -2 plus 8. Okay, just remembering it can be easier to be thinking of it up here because that's -2 divided by -3 squared plus 8. So we get y equals -2 over 9 plus 8. Okay, and that means that y equals 7 and 7/9. Okay, to find our x-intercept, okay, we let y equal 0. Okay, so we go, well, we've got 0 equals -2 outside it. And again, sorry, it's actually probably easier using this first format. So we say we've got 0 equals 8 minus 2 over x minus 3 squared. Okay, because what we'll do is we'll take 8 away, have -8 equals -2 over x take 3 squared. Get rid of our negatives. Okay, for a start, then we're going to multiply by this and divide by that. So we're going to get our x minus 3 squared equals 2 over 8. Okay, or 1 over 4. Okay, so I'm going to come up here now, say that we've got our x take 3 squared equaling 1 over 4. This means we get x take 3 equaling plus or minus a half when we take our square root of a quarter. Okay, so that means then we've got x equals a half plus 3 or negative a half plus 3. So x equals 3.5, okay, or 2.5. Okay, so we've actually ended up with 2 x-intercepts, which when you think back to what our one here is going to look like, okay, it's been reflected this way, but we're going to move it up 8, so we'd expect to get 2 x-intercepts. So we've got everything that we need now to be able to actually sketch this. Okay, we know we're going to have a vertical asymptote at 3. Okay, and a horizontal asymptote at 8. Okay, we also know that we've got a y-intercept at 7 and 7/9, so we know we're crossing very close to our asymptote there. Okay, and we've got an x-intercept at 2.5 and one at 3.5. Okay, so now we can sketch our graph. Okay, so we'll look something like that. Okay, with our axes labelled. Okay, we'll keep moving on. Okay, so we've got the square and cube root functions. Okay, so here we've got our axes shown in the blue. Okay, in the black we have y equals square root of x. Okay, and in the red we have y equals the cube root of x. Okay, so we should all understand that we can't take the square root of a negative number. Okay, so we don't get anything for the black graph on this side. We can, however, take the cube root of negative numbers, so we get this full graph here. Okay, if we're looking at just the square root function, okay, here is again our y equals the square root of x. Okay, this part here is going to be y equals negative the square root of x. We're being reflected in the x-axis. Okay, over here we've got y equals the square root of negative x. okay, because all these negative values, okay, have now been times by -1 to make them positive values. So we get this part of the graph here, but we won't get anything else. Okay, and then this one is y equals negative the square root of negative x, is this one down here. So all of these are separate, distinct graphs. Okay, if we look at them in the form that we have been looking at them, then we get y equals a outside of x take h to the power of a half plus k for our square root. Okay, at the end point, k will be at hk. The domain will be from h to infinity, including h. And if a is bigger than 0, the range will be from k to infinity. Or if a is negative or less than 0, then the range will be from negative infinity to k. For our cube root, then we have y equals a outside of x take h to the power of a third plus k. So we get a point of inflection, okay, because it is very much like a point of inflection, okay, at hk. And the domain and range are both r for those ones. So we'll have a quick look at a worked example. Okay, we'll look at sketching a graph again. So we've got to sketch a graph of y equals the square root of 4 take x take 1. Okay, so say we've got y equals minus x plus 4 to the power of a half take 1. Okay, and if you have seen some of the other tutorials I've done, you'll see that we've got a way of dealing with this negative inside. What we do is we take it as a common factor. Okay, and the reason why we do that is, sorry, that should be a 4, is if we don't, okay, then we're going to translate the wrong way. Because here, if it's positive, we think, oh, we moved to the left. Okay, but in reality, because it's negative, okay, we've got to take it as a common factor and we're going to move it to the right. Okay, so our endpoint in this case is going to be at 4, -1. Okay, so we've got pretty much, no we don't, we need our x and y intercepts, because it's been translated, we'll get x and y intercepts. Okay, so we'll start off with our y intercept, so that's when we let x equal 0, so y equals the square root of 4 minus 0 minus 1, which is y equals square root of 4, obviously 2 take 1, okay, will give us 1. Okay, and our x-intercept, okay, is when y equals 0, so we say that we get 0 equals square root of 4 minus x minus 1, so 1 equals square root of 4 minus x. Okay, so we end up with 1 equals 4 minus x by squaring both sides. Okay, so then we get minus 3 equals minus x, so x equals positive 3. Okay, so now we have everything that we need to sketch our graph. We know our y-intercept is at 1, our x-intercept is at 3, and then at 4, and at -1, we're going to get our endpoint. Okay, so a graph is going to look something like that. Okay, we've got one last section to look at, okay, which is power functions in the form of y equals x to the power of p on q. Okay, so remember we can think of this being written in a different way because of our index laws. Okay, we can think of it as the q root of x to the power of p. Okay, so if p is bigger than q, the polynomial shape, okay, will dominate. So this x to the power of p shape will dominate over the root shape. Okay. However, if q is bigger than p, okay, then the root shape will dominate. Okay. And if p equals q, then the function is just a straight line. It's a linear function. Okay. So even roots of x to the power of p don't exist for x is less than 0. So remember, if we've got even roots, we're talking about square root, fourth root, sixth root, that sort of thing. Okay. And we can't have negative values. Okay. The points 0, 0 and 1, 1 are always lie on the graph. Okay, and what we've got here, it's just a little bit of a demonstration of what the different graphs look like. So we've got our axes here, we've got 0, 0 and 1, 1. All three graphs go through 1, 1. You see that our black line here, this is our line y equals x because p equals q. Okay, so when p equals q, they're going to just cancel out and make it 1, so it's just going to be y equals x. Okay, here we've got the case where p is bigger than q. As we said, the polynomial shape dominates. Okay, so it looks like a nice polynomial. Okay, where down here we've got q is bigger than p, and you see the root shape dominates. Okay, so we've got one last worked example, which is just we need to just decide on what the shape of the graph will be. Okay, for two functions. So we have y equals x to the power of 2 on 3. We need to think of what that shape is going to be. So we look back. Okay, so p is on the top, q is on the bottom. Okay, so which is bigger? Is p bigger than q? Is q bigger than p? Okay, well, our q is going to be bigger than our p in this case. So when our q is bigger than our p, the root shape is going to dominate. Okay, the root shape is going to dominate. Okay, if we have a look at the next one though, it is y equals x to the power of 3 on 2, and this time p is bigger than q. Okay, so the polynomial shape is going to dominate. So for this one, we'd end up with something that's along the lines of this. Okay, for this one, however, though, we'd have something that goes along the lines of that. Okay. So that's the end of this tutorial, so that's hopefully enough to get you through this section.